We'll now move on to Project 2.02, which is also concerned with feature extraction with perhaps a little more topographic and an imagery focus. And the presenter will be Dr. Chunsun Zhang, who's the project leader of 2.02. Chunsun, please.
Thank you. Good morning, ladies and gentlemen. Welcome to my presentation. The project 2.2 follow the project 2.1 presented by Jeff. We dealing with feature extraction, but we are using the data from the different platform. Specifically, we use the data acquired from the airborne platforms. The project work today is performed by myself and my colleagues Mohammed and Yu Xiang and Abadat under the supervision of Professor Clive Fraser in the University of Melbourne. Today, this presentation, I would like to have firstly give a brief overview of the project to refresh you guys' memory of what we do and how we plan to do, and then I will focus on our recent progress. Then I give some result. I will also give a few words on our current research. As you see the slides, we work on the feature extraction from the airborne data. More specifically, we would like to transform, develop the algorithms and the computation systems to transfer the remote sensing data into spatial information products like this one shown in our slides. Certainly, we focus on topographic objects and we work on 3D. We would like to achieve a higher level of automation. Definitely, this is a difficult task. Automated extraction of features from remote sensing imagery has been a topic for decades. That's still an active topic today. So we have proposed a 3D image approach to advance this research. So on one hand, the remote sensing data integrated to generate a 3D image, while the 3D image contain the same information as much input as possible, and also the information inside the 3D image are reliable and redundant, which facilitate the processing by the image process feature extraction algorithms to generate spatial information products. More specifically to our current target on the automated reconstruction of buildings, we fuse and integrate airborne imagery and LiDAR data to generate 3D images showing here in the middle. You can see with these 3D images, the buildings are well presented, and the features of building features like corners, like the building corners, lines, and the surface are prominent, so they can be robustly extracted by the image processing algorithms and also combined to generate 3D models of buildings. In line with this general strategy, our recent effort has been made to implement this 3D image concept, implementation with 3D image concept. Certainly, on one hand, we have to combine the data, in particular the imagery and point clouds, and on the other side, we have to develop the robust algorithms for feature extraction. This will be outlined in the following slides. So essentially, the registration of different remote sensing data is a core part of the integration of the image for the generation of a 3D towards the implementation of a 3D image concept. There are a huge number of research in the image registration based on like a feature-based approach or area-based approach. And some of this method has been implemented successfully to the registration of imagery acquired from the same type of sensors. But they usually fail to integrate the data acquired from different type of sensors, for instance, to registration of 3D point clouds and optical imagery. In the laser data point clouds, so the real world is represented as X or Y, Z coordinates, while the optical imagery is a record of reflectance of the real world. So essentially, they are basically different things. And it certainly is difficult to handle. And that's why the most approach available does not work. So we have explored the mutual information technology. We are not looking for physical correspondence between the data set. We actually looking for the statistical dependence between the remote sensing imagery. So the registration will be performed by the maximize the mutual information between the variables, in our case, data sets, in particular the 3D point clouds and the imagery. So we developed a new approach to improve the performance of traditional mutual information technology. We call the general weight mutual information technology. You can see in these slides, on the left side, we have also rectified imagery, and also the point clouds, which represented in the grid format. It's a grayscale in the grid format here. They overlaid together. You can say, well, the data are quite close, but they show significant discrepancy, as shown in this red circle. And with application of our general weighted mutual information technology, we can bring these two data sets aligned quite nicely. You can see here the alignment of is more clearly shown in these slides. Probably it's more evident with these edges buildings here. Before the registration, you can see the discrepancy here and here, while the algorithm bring them align very nicely here. I mean, at least the discrepancy are minimized. So this certainly is an essential part to integrate the data towards the implementation of a 3D image. On the other hand, as I mentioned, we certainly this kind of research is still under improvement to apply to the different data sets. On the other hand, current effort focus on development of new robust algorithms for the detection of or reconstruction of buildings. So this is the wonderful effort we have shown here for improved detection of buildings from the remote sensing data. This work has been built on the previous experience. So we, in this new system now, we incorporate the new algorithms to process more, to extract more features to support the building detection. In particular, we use entropy from imagery, and also we use this edge orientation information to differentiate the buildings and the trees. As we know, in the LiDAR data, the buildings and trees are the two main objects which are above the ground, and it's difficult to differentiate. So this is the algorithm for the image entropy, and particularly we use this kind of approach to separate the building, separate the trees with the buildings. Some buildings have this green roof, which show the similar reflectance like the trees. Using normal approach, it's difficult to separate them, and we find that this entropy approach has shown the kind of efficiency for this purpose. Another one is use this edge orientation. A lot of people using the image edges for the reconstruction of man-made objects, because usually man-made objects like buildings and roads have long, strong edges compared with other objects. But here we make further effort, not only use this kind of geometric edges or shape, we also use the distribution of the edge orientation. This is based on the observation, like the buildings. They usually have the outline of buildings. They usually have rectangle angles. So the orientation of the edges in the histogram will show a 90 degrees difference, and this is perfectly shown in here. While we also got a lot of short edges on the trees because the tree leaves are short. But Also, if you compare this distribution of the orientation, you can say, while the building edges demonstrate this kind of regular shape, while the trees have this random distribution of the edge orientation. So this is a strong features in the image space to differentiate the different the man-made objects and the trees. So the result, to combine this kind of feature extraction into the building detection, we got a significant improvement as shown in this slide here. We got the data approved in Melbourne and also in New South Wales. You can see the result, it's quite good. We got over 95% the correctness in the companies. That means over 95% of buildings are fully automatically detected by our system using this new approach. This approach also is particularly efficient in the mountainous area with a lot of trees. You can see here on the left side is an approach based on our previous system. We got a lot of false alarms here. While with the improvement was significant. You can see here, a lot of this false detection are removed. So you can see this is a significant improvement in our new development. Certainly, the performance of this algorithm increase, with the quality of data. This is one of the data set provided by our partner. They fly very dense LiDAR data, and they got a very high-resolution area imagery, so the result is even better in this case. Almost all in this example, almost all the buildings are fully automatically detected. In addition to the image processing, we also made the effort to processing the point clouds. We developed a new approach, we say the plane-based approach to segment the point clouds. Why we use plane-based? Because we are interested in the man-made objects like buildings. The building roofs usually have a composed of different planes. And in addition to that, even the ground surface, they are locally flat. They can also describe a plane. So we developed such kind of approach. Certainly, this the laser scanning, the processing of laser scanning data attracted a lot of interest recently. There are commercial software available to do such kind of job, but the performance of commercial software, probably you guys have experienced, they varies with the different terrain, with the density of data. So we want to make some effort in our research to improve that. So this is the basic procedures we use. We go with the cluster segmentation, as we said, the plane-based, and then we classify and group the laser points based on the spatial characteristics in relation to the neighborhood points. So the goal is wanted to make a robust detection of theta points over the plane, so we know where to generate plane. And then we want a robust approach to avoid the outliers, errors, to generate a plane with a higher accuracy. And another one is, as we said, we have plane on the ground, we have plane on the top of buildings. We want to make a clear classification. So which planes that belong to the buildings, which planes that belong to the ground. So we can concentrate on the planes which belong to the buildings for our building reconstruction purpose. The last one, we want to use this kind of the plane using the statistical approach to generate geometrically accurate and topologically consistent the building models. We classify and group the points, laser points, using this principal component analysis techniques, showing. So we generate, at the beginning, we find, okay, which points belong to the plane, has a high potential belong to the plane, which points are not. So we can easily exclude such kind of points from the beginning. I demonstrated this algorithm use a data set provided by our partners. So the first one, you can see with a very high density, 35 points per square, which is around 16 to 17 centimeter in the ground spacing. Another one, you see the density is much lower, only 5 points. Here, this is in Queensland, this is the campus of Melbourne Uni. Again, each of the data set include many buildings, trees, and other man-made objects like power lines here. This is the first example showing here the detection of plane points. The algorithm works very well. You can see here on the roof, we get these plane points showing in red full automatically. We also detect the points at the edge, at the intersection of two planes. So these points they have demonstrated linear characteristics, so they are not classified as plane points. The problem is, you can show here, this is the trees, and here's the ground. The ground is generally flat in this area, so the ground is detected as a plane, while the trees are well separated, because the trees, even if they got very dense points, but they can't form a plane. So this kind of processing facilitate the segmentation of point clouds. And based on this detected plane points, we can group the points into planes, which is very good for building interaction. You can see here the roofs of buildings successfully grouped, also showing here. And because the ground are flat, they will also detect the ground. So this approach can be also used to segment the point clouds for the separation of objects above ground and on the ground. I didn't show here such a kind of approach can also use to detect with a higher density of a point cloud. We can also use it to the detection of power lines, like this kind of energy facilities. We made a further research in the point cloud processing, not only for the generation of the planes, roof planes, but also we try to generate reconstructed building walls, which has never tried from my knowledge by our society. We know the density on the building on the walls are quite low compared with the roofs, but we still can pick up many walls. You can see this is a data set. Most of the walls are not extracted, but also more geometrically modeled nicely. This is an example with a low density data in Melbourne. You can see the point clouds are processed to detect the plane points, which is represented in red. And here is a detection of the roofs, which are also the planes. So we'll just show here the algorithm's performance are equally well with a different density of laser point clouds. So this kind of effort has this effort was made in the last several months towards the implementation of 3D image concept to facilitate the reconstruction of buildings. Certainly, we have a lot of exciting challenges in front of our project. I just point a few over here. Still, we want to complete the 3D image concept from one side for the data integration, on the other side to develop more robust algorithms for automated reconstruction. This is the algorithms. Our goal is to integrate all the processing in one platform, which we have here in our project point 2, which is a Brista. Probably many of you have known this one. Some companies probably have used this one, for high-resolution satellite image processing. Okay, this is my report today, and I would like to thank my partners of the project. I appreciate the cooperation with them. Thank you.
Thank you, Chunsun. We'll allow just one question.
We use this PCI because it's a theta point. We find a lot of theta points, not only one. And based on this group points, we have or filter. We group them, and we find we certainly we didn't use this robust PCA, but after our PCA analysis, we filter this group points. We find a very reliable one, because for theta points we just need only one. We don't need all of them. So this is why the works, I know we still have few outliers in our laser data, but that's why we still works well in the plane extraction.
Thank you very much again, Chunsun.
Thank you.